So welcome back. I kind of wanted to let you know, as I was looking through your textbook, you will notice that when they talk about speech perception, they talk about some different models such as the trace model or the cohort model. I'm not really going to talk about those very much. I think they're a little bit complex for you. Now, I am going to show you some scarier models when we get to reading, but by and large, these aren't necessarily things that I will test you on. For those of you thinking about taking the final, don't worry about the trace model, don't worry about the cohort model. Stick to what we're talking about here, and I think you'll be fine. So let's move on to our discussion of speech perception. So one of the other things that we find that tends to happen is something called a lexical identity shift. So when we are recognizing words in a stream of auditory speech, this requires both bottom-up processing and top-down. And by and large, anytime that we're navigating stimuli in our environment, we are never purely using bottom-up information and we're never purely using top-down. We're using both to try to process things as quickly as possible. And so one of the ways that we can kind of see this interaction between bottom-up information and top-down information is with something called the lexical identification shift. Generally, what we're going to find is that if I give you an ambiguous phoneme, such as pleh, so it's not quite T and it's not quite D. So it's not quite T and it's not quite D. So we're using processing there. But what we're going to find is that that ambiguous phoneme is often going to be categorically decided or assigned to a given phoneme if it forms a word. So if I present you with an ambiguous phoneme that is basically stuck between t and duh, so th, odds are you're going to be likely to assign it to a d than to a t. And that's because dash is a word. Tash, save for that colleague that worked with Dave Pizzoni, is a word, we're going to be more likely to assume that that ambiguous sound was a D. So that's the case where top-down processing, our understanding of words, helps us interpret this bottom-up information. So context does appear to influence categorical perception due to how we perceive things and how we process things. So it is a combination of bottom up and top down. We also do use the context of the sentence itself. Generally, the identifying phoneme is going to be influenced by the meaning of the surrounding sentence. This is what we call a sentential context. The problem with this is that we can only make that justification after we have perceived the speech signal. So this is going to come with a little bit of a delay. So one of the other things that we will find is that we can use sentence context to help us interpret phonemes. One of the ways that we do this is with the phonemic restoration effect. So the perception of an ambiguous phoneme ends up being based on the sentence context. So for example, if I give you a sentence like the heel was on the axle, you're going to interpret that cough as a W. On the other hand, if I say that was on the orange, you're going to assume that that cough was a P sound. So the peel was on the orange, the wheel was on the axle. So this is something that Warren and Warren actually did with participants in 1970. So they would give them an auditory sentence, but one part of the sentence was covered up with a burst of white noise. It basically sounded like this, like static. And then based on the context of the sentence, people would identify the phoneme differently. So if it was the heel was on the axle, they'd assume the sound was a W. If they heard the heel was on the shoe, they'd assume it was an H. So we basically used the rest of the sentence to help figure out and fill in what that missing phoneme was. And we're not quite sure what causes this effect. It could be due to the top-down processing from the sentence, but it could also be due to the bottom-up processing of the static sound. So this can be due to direct and indirect effects of speech perception. So how do we recognize spoken words? So one of the earliest theories of word recognition in speech, and I would be remiss if I didn't share it with you because, folks, this is probably one of the more ridiculous theories that we've talked about besides Biedermann's recognition by components or Gibson's theory of direct perception. This is what's called the motor theory. And so the motor theory basically says we are able to figure out and segment words in the speech signal because as somebody is talking, we are mimicking the articulation and the articulatory movements of the speaker. So as I am talking to you, according to the motor theory, there is something inside of you that is mimicking every single one of these movements that you hear me making. And the reason that they argued that this was what had to happen is that generally a motor signal is going to be more consistent and more invariable, that means less likely to vary, than speech is. And here's some of the support for this theory. So Dorman and colleagues presented people with a word like shop, but if they made a pause prior to the word shop, most people mishear it as chop. Now, that actually kind of fits with the motor theory. You don't necessarily have to take a very long pause before you say the word shop. You do have to take a slightly longer pause to say the word chop, because you have to get that ch sound rather than that softer sh sound. So that's some evidence. Additionally, Fadiga and colleagues back in 2002 actually found that people, when they actually tried to do muscle measurements for muscle movements in the tongue, they actually found that for people who were listening to words, they actually found greater activation of the tongue muscles when people were hearing words that actually ended up involving more tongue movements, like the word involving. But let's be honest, this is a weird theory, and I don't necessarily buy it. I share it with you because it's funny and it's kind of interesting, but there's a lot that motor theory cannot explain. First of all, how on earth does auditory information actually end up being translated into a motor movement? Additionally, people who have deficits with speech production, such as something like Broca's aphasia, where they have damage to the left inferior frontal gyrus, they can still comprehend speech. Technically, the motor theory says that if you can't produce those articulatory movements, you have no speech comprehension. And data from Broca's aphasia, people with that aphasia, that is clearly not true. They are able to comprehend, they just don't have the ability to produce. Additionally, here's an additional piece of evidence. Infants are not able to speak and produce language well up until about 12 months of age. And yet, despite that, even very, very early on, they can detect differences in syllables despite not actually having the capability to produce speech at that point. So the motor theory, while interesting and potentially intriguing, does not work for me. I really don't think that as you're listening to me talk right now, you are mimicking my mouth movements. So yeah, that's the motor theory. I will talk just briefly about the cohort model, but I'll try to keep it pretty short. So this was developed by Marslen, Wilson, and Tyler back in 1980. And so the cohort model is basically the idea that when you are starting to hear speech, initially you are going to, this is kind of a spreading activation model, you are going to spread that activation to all words that conform to the early part of the sound sequence. So when I say buh, activation is going to go to bell, ball, bill, bowl, etc. And you're going to have a lot of competition between items. As you get more information, so as I go to bill, all of a sudden I can get rid of ball, bell, bowl. Now I've got words like bid, bill, big, etc. And so the idea is that as I get more auditory information, I'm basically eliminating more and more information that doesn't fit that. And so you're eliminating items until you get, until only one word remains. This is basically what Marslen, Wilson, and Tyler refer to as the uniqueness point. And all of this is based on parallel and interactive processing. So some that we have for the word monitoring task, so we have word targets that are presented in different types of sentences. So in the very first experiment of Marslen, Wilson, and Tyler back in 1980, they basically had different types of target words, either a target type that matched a word or that rhymed with a particular prime or fit within a certain category. So there were 3 different types of sentences that were actually used here. So what you're looking at here, one was called a syntactic prose sentence. Basically, all of the content words from a normal sentence were replaced with different content words with new words of the same type of form and frequency. So the resulting sentence had a syntactic structure, but it actually had no meaning. Here we have a normal sentence that we might get in prose. Here's a random sentence where there's no meaning and there's no syntax here as well. So again, we have a normal sentence, a sentence that has the proper syntactic structure of subject, verb, object, but doesn't really mean anything, and then no meaning and no proper syntax whatsoever. In addition, they had to do a word monitoring task, and there were 3 different types of tasks depending on the situation that they were told to do. For identical monitoring, the particular cue word was the actual word that they were supposed to listen for. So for example, the identical cue word was lead. So if they heard lead, they basically had to identify that. If they had a rhyme monitoring, the subject had to listen for a word that rhymed with the cue word. So in this case, that might be a word like breed, or it had to be a word that was a category. So a lead, something that would kind of fit within that category, but not the same word, such as direct. And so what you can kind of see here is that in general, when we're doing identical, it really doesn't seem to make a lot of difference what sentence type you have. But one of the things that you'll notice is that as we move further away from having the help of sentence context and proper meaning and proper syntax, words get much harder to identify. That's especially true for sentences that have syntax but no meaning, as our syntactic sentences do, and then random sentences that have no syntax and no meaning. So based on this, there's the revised cohort model. Your book talks about an even newer model called the distributed cohort model. So the cohort is basically the idea that words vary in their level of activation. It depends on how often you use them. It depends on context. For me, a lot of psychology-based words or cognition-based words are probably going to have more activation for me than they might have for you, and that's because I use them more frequently. Cohort membership, whether or not we include them as part of a potential word that could be used, is based on degree. This will include words with similar matches to the initial phoneme. So the example that I gave was b. It could also potentially include v, which sounds very, very similar. And it does actually place a greater emphasis on bottom-up processing than the previous model did, because context effects do tend to occur a bit later. So this is definitely better than motor theory, at least. So the pros of the cohort model, we're rightly assuming that items compete with each other as we're trying to process what word was said, and there is parallel processing, and this better explains rapid identification. Your book says that this is a sequential process, but the distributed model kind of suggests that some of this is occurring in parallel. Research has found that there's probably earlier contextual modeling than we tend to give it credit for. The cohort model says that context comes in really late, and there's a lot of evidence that context comes in earlier than we thought. The revised model is less precise and it's harder to test. And we also don't fully understand how early identification of words in the speech signal take place. So there's some work to be done. So yeah, I am going to talk about the trace model very briefly. I'm not going to test you on it though, just so we're clear, and I'll keep this short. So the trace model is a connectionist model. And so basically we have different types of levels when we're processing sounds. So we have the word level, we have the phonemic level, and then we have different features of those phonemes. So is there a stop, a flow? Is it a powerful phoneme? Is it voiced? So what do we mean by voiced? I mean, for certain phonemes, you will hear your vocal cords basically vibrate. So go ahead and take a hand to your throat and go, You should hear your vocal cords. And yes, I know they're folds, but I'm calling them cords. You'll hear your cords vibrate. If you do something like B, you'll hear it vibrate. If you go sh, you won't hear them vibrate. So when you hear them vibrate, that means they're voiced. If you don't hear them vibrate, they are not voiced. So the idea is that this is a parallel processing model, and these nodes are going to influence each other in proportion to their activation levels as well as their connection strength. So if I hear this kind of word, it is going to send activation out to certain aspects. So this is bass, so it goes to B, goes to A, it goes to S, and it's going to send information out to those features. Additionally, as you are actually hearing this speech, activation is being sent from the features to the phonemes to the words. So a pattern of activation or a trace develops, and the candidate with the highest activation then becomes the recognized word. And notice too that this activation does spread. So what evidence do we have for the trace model? We have something that is called a word superiority effect. This is basically the finding that it's a lot easier for us to identify a speech sound if it actually forms a word than if it doesn't form a word. So top-down processes can explain why items that form words are easier for us to identify. This has actually been successfully simulated with a computer. Additionally, there is evidence of top-down processing, and this does affect how we categorize phonemes. And additionally, research that has looked at eye gaze, generally there's evidence for this competition and this activation. Eye gaze is largely captured by high-frequency word distractors. And this is because high-frequency words, these are words that we tend to use more often. And because we use them more often, they tend to have a very high resting level of activation. If somebody says a word, it's probably going to be high frequency, and because we know that, its resting activation level is going to be pretty high, and we tend to look more and focus more on those high frequency words. So evaluating that trace model, it does account for various speech effects such as the word superiority effect, the greater emphasis on high frequency words, the lexical identification shift. We're likely to assign a phoneme to a particular group if it forms a word versus a non-word. There is emphasis of interacting top-down and bottom-up processes. We know that's happening. Additionally, it does cope very well with very noisy input. Here are some problems. It exaggerates the importance of this top-down processing. It tends to be too flexible. We've used this on a very limited set of stimuli, and this doesn't really tell us much about things like writing or reading or non-phonemic information. So now, let me see. So I was supposed to have a slide for reading, but alas, I do not. We're going to go ahead and stop here, and we will talk about reading next time.